We are born inside time. We wake up within it. We age because of it. Yet we rarely stop to ask what it actually is. Time feels obvious. Time feels steady. It feels like the universe keeps a perfect beat. Every second, the same length, everywhere. It feels natural to believe that someone standing on a distant mountain, a pilot crossing the sky, and an astronaut drifting over Earth all experience time flowing in perfect sync. We assume that the ticking of clocks is universal. That one moment here is one moment everywhere. Such a belief is comforting. It gives us order in a world that often feels chaotic. The idea that time could behave differently depending on where you stand almost sounds like fiction. After all, a second is a second. We measure it. We count it. We plan our entire lives around it. A second does not stretch. It does not shrink. It does not change its mind. That is how we feel. But feelings are not physics. Physics does not care about what seems reasonable. Physics cares only about what is true. For centuries, we imagined the universe as a grand mechanical stage. Events happened on this stage as if an invisible conductor kept time with perfect rhythm. The English scientist Isaac Newton believed that time existed independently from everything else. To Newton, time was absolute. Time flowed forward without interruption. Time flowed the same for every observer, regardless of location or motion. Time was like a river that could not be altered or slowed or sped up. Newton assumed that the rules of the universe were fixed and eternal. Space was the place where everything happened. Time was when everything happened. The two had nothing to do with each other. That picture dominated our understanding for generations. It fit our daily experience. Life seemed to confirm Newton's certainty. You drop an apple, it falls. You place a clock beside another, they tick together. Nothing suggested that time could bend. Nothing suggested that time could behave like anything other than a rigid cosmic beat. But then came a young patent clerk in the city of Bern. Albert Einstein looked at reality from a different angle. While sorting technical papers, he played thought experiments in his mind. He asked himself questions that others considered unnecessary. What would the world look like if you chased a beam of light? What happens to time if two observers move differently? What if the speed of light never changes no matter how someone moves? Einstein realized that if the speed of light is constant, then something else must give way, and that something is time. If you move fast enough, time must slow down relative to someone who is not moving. Einstein proved mathematically that two observers in different states of motion do not agree on time. Their seconds are not identical. Their clocks do not tick at the same rate. Time is personal. Time is relative. Imagine two twins. One stays on Earth. The other travels far into space at tremendous speed and returns. The traveling twin has aged less, not just in theory, in reality. Their biology has experienced fewer moments of time. Their heartbeats have existed inside a slower rhythm. Time literally flowed differently. This idea sounds like a trick of language. It is not. It is a fact confirmed by experiment after experiment. The faster you move, the slower time passes for you. Einstein called this special relativity. Motion affects time, but he did not stop there. He pushed deeper. What if something other than motion could bend time? What if something could warp the fabric of existence itself? Einstein wondered how gravity truly worked. We are taught that gravity is a pull. We drop something and gravity pulls it downward, yet Einstein saw something deeper. He pictured gravity not as a force, but as the result of curved space. Massive objects deform the fabric of space around them. If you drop an object near Earth, it follows the curve created by Earth's mass. The object is not being pulled. It is simply following the shape of space. Space tells matter how to move. Matter tells space how to curve. But Einstein's revelation did not stop with space. If space can bend and time is connected to space, then time must bend as well. Gravity affects time. The stronger the gravitational field, the slower time passes. A clock near Earth's surface ticks slower than a clock high above Earth. The difference is small but measurable. If you place two identical atomic clocks, one at sea level and another on a tall mountain, the clock on the mountain runs slightly faster. The difference is not a metaphor. It is real. Time itself is flowing differently. This means something profound. Time is not universal. Time is not absolute. Time depends on where you are and how fast you are moving. Time is not a passive background. Time is woven into the structure of the universe. Time is part of the fabric of reality. To understand how radical this is, imagine that you are standing in a vast empty space. There is nothing around you, no planets, no stars, no light. You set a clock in front of you and watch it tick. The seconds pass. They feel smooth and even. Now imagine that a massive object appears nearby. Space curves toward it. And suddenly your clock slows. Nothing touches it. No force is applied. Yet time slips into a different rhythm. Your heartbeat slows relative to someone far away. If you leave the massive object and travel outward into emptier space, time speeds up again. Not metaphorically, literally. Your moments become shorter. Your life runs faster. But you do not feel any of this. Time dilation is silent. It does not announce itself. It simply happens. We want time to be fair. We want time to treat everyone equally. But the universe is not interested in fairness. Time depends on the shape of the cosmos. Where there is mass, space bends. And where space bends, time bends with it. The truth is simple. You are living inside a flexible fabric. Your life is not just a movement through space. Your life is a movement through space-time. Every choice you make is a line you carve into that fabric. Every breath exists within a structure that responds to motion and mass. You do not simply pass through time. Time twists around you. And if time can bend, then time can be shaped. It can be stretched. It can even nearly stop under the right conditions. If you stand close to something unimaginably massive, like a collapsed star, time for you would run so slowly that the rest of the universe would race forward. Your seconds would not match anyone else's. Someone far from that intense gravity would live out an entire lifetime, while you would barely age at all. This is not philosophy. This is physics. Measured, verified, proven. Your personal flow of time depends on your place in the universe. You are not experiencing time the same way as someone at another altitude or moving at another speed. Your now is not there now. The universe does not agree on a single present moment. Time is local. Time is personal. Time is relative. And if time is flexible, then the next question becomes unavoidable. What is bending space and time? What hidden shape holds the universe together? The answer is gravity. Time is not something you travel through like a passenger on a train. Time responds to you. Time reacts to you. It reshapes itself according to your motion and according to gravity. Most people think of gravity as an invisible pull from Earth. You drop something and gravity pulls it downward. But that explanation only scratches the surface. The deeper story is stranger and more beautiful. Gravity is not a force acting on you. Gravity is the shape of space-time guiding you. Imagine a giant trampoline stretched tight. Place a heavy ball in the center. The fabric curves downward under the weight of the ball. Now take a smaller ball and roll it near the heavy one. The smaller ball does not move because the larger ball pulls it. It moves because the fabric slopes. The smaller ball merely follows the curve. Now replace the balls with planets and stars, and the trampoline with space-time. Einstein discovered that mass tells space-time how to curve, and curved space-time tells matter how to move. The fabric does not only control where objects move, it controls how time flows for them. If you stand near a large mass, like Earth, you stand where the fabric dips. Time slows there. If you move farther from the mass, time speeds up. Time flows fastest where the fabric is flat and empty and far from any gravitational influence. The closer you are to a massive object, the slower your time runs. The farther away, the faster it goes. At first, this seems irrelevant to daily life. The difference in time flow between sea level and a mountain is very small. But the important truth is that the difference exists at all. If time can stretch even a tiny amount for a tiny change in gravity, then in extreme gravity, time can change dramatically. In ordinary life, you are used to clocks that match. You are used to people around you living inside the same rhythm. Yet the universe does not synchronize anything. You are in your own river of time. Everyone else is in theirs. Consider a person standing on a mountain. Their altitude places them a bit farther from the center of Earth compared to someone at sea level. Gravity is slightly weaker for them. Weaker gravity means time flows a tiny bit faster. Over a human lifetime, the difference might be only a fraction of a second, but the difference is real. The person on the mountain ages slightly faster than the person at sea level. Now imagine that instead of a mountain, we think of a planet with gravity far stronger than Earth. There, the slowing of time would be substantial. A person standing on the surface of such a world would live through fewer moments of time compared to someone far away in empty space. If two people who began at the same age were separated, one sent to a region of intense gravity and the other kept far from any mass, the difference in aging would become visible. One would grow old, the other would remain young. Time bends so easily that we do not notice it. Everything around us is flowing within the curved fabric created by Earth. We are already living inside a warped reality. Every step we take, every breath, every thought is happening inside a river of time that is shaped by gravity. To understand how shocking this is, think of the most ordinary moment. Standing in a room, the clock on the wall ticks, the seconds pass. Now imagine that same clock deep underground, closer to Earth's center. In that stronger gravity, the clock slows slightly. Even though the clock looks identical and ticks in the same way, it measures fewer moments. Its version of reality has fewer slices of time in each passing minute. Your body does not feel this difference. The clock does not feel anything, but the universe notices. Time is woven into the universe just as threads are woven into cloth. If you press the cloth, the threads shift. Press space-time with mass, and time shifts. Einstein had no giant clock in space to test his idea. He relied entirely on logic and mathematics. He trusted reason over tradition. He predicted that gravity slows time long before any experiment was precise enough to detect such a tiny effect. His theory waited patiently for technology to catch up. Decades later, atomic clocks made the invisible visible. An atomic clock counts the vibrations of atoms. Each vibration is identical and reliable. Atomic clocks are so precise that they would not drift by even a single second over millions of years. When scientists compared two atomic clocks at different altitudes, the upper clock ran faster. Time flowed differently. This was proof, not metaphor, not imagination. Proof. And yet, despite that proof, we still cling emotionally to the illusion of absolute time. We live inside a linear story. The day begins, the day ends. We measure our lives by the ticking of clocks. We believe that each second is uniform, identical, predictable. We feel time as movement, but time does not move. Time simply exists as part of the fabric we inhabit. Einstein showed that time is not a river that flows. Time is a landscape, a terrain. The shape of that terrain depends on matter and energy. When you move, you trace a path through that landscape. The shape of space-time can stretch those paths, or compress them, or twist them. If someone asked you where you are, you could point and say here. If someone asked you when you are, you would say now. But here and now are not separate. They are coordinates in space-time. Move to a different location, and you change the shape of your path through time. Move with more speed, and you change it even more. Time is not a constant background. Time is dynamic. Every second that passes is not fixed. Every moment is not identical. Time is part of a fabric that bends. Imagine walking across a vast field. If the field is flat, you move easily. If the field slopes, your path takes longer. Time is the same. In regions where space-time is curved, time stretches. In regions where space-time is flat, time shrinks. Your clock records these differences, even if you cannot sense them. The universe does not care about your intuition. The universe operates only by reality. Reality is stranger than intuition. Reality bends time. When we next step deeper, we will see that if gravity can slow time, then extreme gravity can reshape time nearly to the point of stopping. We will follow this idea into places where the universe folds in on itself, where the flow of time becomes so distorted that your future and someone else's future separate into different realities. The illusion of constant time ends here. Next, we reveal what gravity truly is. Gravity reshapes time, yet that single sentence barely captures how strange the universe truly is. The more we look, the more the familiar world begins to wobble. Everything we assumed was solid becomes flexible. Everything we believed was constant becomes relative. Time is not a single universal pulse. Instead, time behaves like a living fabric, shifting and stretching in response to anything with mass or motion. Think again of that smooth trampoline surface representing space-time. When you stand on it, you barely dent the fabric. You are small. Your mass creates only a tiny curve. Earth makes a deeper impression. The sun pushes down farther still. A giant star creates a crater. In every case, the shape of space-time changes. And when the shape changes, the flow of time changes as well. The deeper the curve, the slower the time. This is not a metaphor for thought. It is a description of how the universe actually behaves. Everything that exists falls through time at the speed of time. In the emptiest regions of the cosmos, where gravity is almost non-existent, time flows freely. It is like a river racing downhill. But when space-time curves deeply, around a massive object, time flows as if moving through thick honey. The river slows, seconds stretch. You already live inside this effect. Everyone on Earth experiences time dilation every moment of their life. Your body and your clock are moving through curved space-time right now. You cannot feel that curvature. You only know gravity as a gentle tug. Yet gravity is not a tug. Gravity is the shape of space-time beneath your feet. When Einstein first presented this idea, it sounded impossible. Time could not stretch. Time could not slow. Yet mathematics insisted that it must, and the universe confirmed it. At high speed or strong gravity, time proves Einstein right. Time becomes a local experience. It does not belong to the universe. It belongs to the observer. Consider a thought experiment. You hold a flashlight and point it straight upward. Light travels at a constant speed. If that light climbs out of a region with stronger gravity and into a region with weaker gravity, the light changes frequency. That shift shows that even the rhythm of light must adjust to the change in time flow. Light itself cannot escape the influence of curved time. If light bends to the rules of gravity, how can we imagine that time is immune? We like to visualize time as a straight line, childhood on one end, old age on the other, a single arrow pointing forward. But imagine that line instead as a thread woven into fabric. The thread can curve, it can stretch, it can tighten. If the fabric is pulled, the thread changes shape. Your path through space-time changes with it. Imagine two astronauts both leaving Earth. One travels straight upward to a point far away from any planet. There, gravity becomes weak. Time flows faster. The other astronaut remains in low Earth orbit. They move fast. Their motion slows their time. They live fewer moments than the astronaut floating far from mass. When the two meet again, they will not agree on how much time has passed. One will have aged more than the other. They may have left at the same moment, but they return from different rivers of time. The shocking thing is that this is not speculation. This is reality. Scientists have measured time dilation using atomic clocks so precise that even the movement of a fraction of a centimeter changes their reading. Raise that clock by the height of a table, and time speeds up. That result tells us that time responds instantly to changes in gravity. The universe always tracks the curvature of space-time. Every atom vibrates according to that curvature. Every cell in your body ages according to the shape of space-time around you. Time is personal. Nothing in your experience is truly universal. Your heartbeat, your breath, your perception of now, all are tied to the path you carve through space-time. You and every person on Earth are drifting through slightly different flows of time. We do not feel these differences because our lives are slow and gravity on Earth is moderate. But the universe contains places where time behaves wildly differently. Einstein once wrote that people like us, who believe in physics, know that the distinction between past, present, and future is only a persistent illusion. At first, such a statement seems poetic, but it is far closer to literal truth than you might expect. If time can move faster or slower, depending on gravity or motion, where do we draw the line between now and later? What does it mean to say two events happen at the same time, if time depends on where you are and how you move? If there is no single now that the universe agrees on, then our experience of time is not the entire truth. It is only our local truth. Pause for a moment and imagine everything you have ever experienced. Every memory stored in your mind, every dream, every failure, every triumph. All of it sits inside the path you took through space-time. Every possibility for your future sits ahead of you on paths that space-time already allows. Your personal story is not written in air. It is written into the fabric. You are not traveling through time. You are sculpting it. This realization changes everything. Time is not simply measurement. Time is geometry. Time is shape. When mass bends space, it bends the flow of time. When you move, you stretch your personal time relative to others. And if time can be stretched, then time can be squeezed. Under the right circumstances, time can approach stillness. To fully appreciate what comes next, you must be willing to abandon the comfort of intuition. The universe does not care what makes sense to human minds. The universe is under no obligation to agree with our assumptions. Time is not constant. Time is not universal. Time is flexible. In the next chapter, we will dive into the true nature of gravity, not as a force, not as an invisible pull, but as geometry. When you finally see gravity as the shape of space-time, everything about time will fall into place. You stand on Earth and feel a downward pull. The pull seems obvious. You drop something and gravity drags it toward the ground. You jump and gravity pulls you back. You let a stone slip from your hand and it falls. Every person who ever lived has witnessed this. So we invented a simple explanation. There must be a force, an invisible tug, something that reaches out and pulls objects together. For centuries, that idea was enough. Isaac Newton studied that pull. He calculated how strong it must be. He described how it acts between objects. If the distance between two bodies increases, the pull weakens. If the masses grow larger, the pull increases. Newton gave us the mathematics to predict the motion of planets, the orbit of the moon, and the trajectory of falling objects. His equations were elegant and precise. They worked so well that the world accepted gravity as a force without question. But Newton himself felt uneasy. He could calculate gravity, but he could not explain it. How can one object reach through empty space and pull another toward it? Newton called it action at a distance. He did not know how it worked. He simply knew that it did. Centuries later, Albert Einstein stared into that mystery and refused to look away. If gravity is a force, then where does it come from? What carries it? Why does it travel? Why should a planet know that another planet exists far away and respond instantly to its mass? Einstein began with a simple observation. When you fall, you do not feel gravity. If you step off a ledge and begin to drop, during that fall you feel weightless. Gravity seems to disappear. If gravity were a direct pull, why would falling remove the sensation of weight? Shouldn't a pull be felt at every moment? Einstein imagined someone inside an elevator cable snapping. As the elevator falls, the person floats. A coin released inside the elevator floats beside them. For those few seconds, the person and the coin experience the same motion. There is no force pushing or pulling inside. Everything is moving along a shared path. They are all following what Einstein called a geodesic, the natural path through space-time. From that moment, Einstein realized that gravity is not a force. Gravity is motion through curved space-time. Imagine the universe as a single fabric, not a thin sheet, not two-dimensional, a four-dimensional fabric made of 3 dimensions of space and 1 dimension of time. Every object, from a grain of sand to a star, sits on that fabric. If the object has mass, the fabric curves around it. The heavier the mass, the deeper the curve. When you drop an object, nothing pulls it. The object simply follows the curve, like a marble rolling along a bowl. It moves not because something tugged on it, but because the shape beneath it directs its path. Gravity is geometry. Space is not empty. Space has structure. It bends, it ripples, it changes shape, and objects do not resist that shape. They move along it. The apple that falls from a tree does not seek the ground. It seeks the lowest point in the curve created by Earth's mass. This idea completely replaces the old one. Gravity is not a thread pulling objects together. Gravity is the architecture of the universe. Mass sculpts that architecture. Objects simply follow the shape. Stop and picture space as a pond. Drop a stone into the water. Ripples spread outward. Space-time behaves the same way. When objects move or collide, the curvature changes. Ripples appear. These ripples are real. We call them gravitational waves. They are waves of space-time itself, shaking as massive objects move. They travel across the cosmos at the speed of light. Einstein predicted these waves long before we had the tools to detect them. In the early years of the 21st century, scientists built detectors capable of measuring changes in space-time smaller than a fraction of a proton. When 2 black holes crashed into each other more than 1 billion light-years away, the curvature of space-time rippled outward. Those ripples eventually reached Earth. Instruments sensed the stretching and squeezing of space. The signal matched Einstein's prediction exactly. We recorded the shaking of reality. Gravity is not a force. Gravity is the shape of space-time. Now imagine something profound. If space can curve, and time is part of space-time, then time must curve along with it. The bending of space is also the bending of time. When Earth warps space-time, clocks slow within that curve. When a massive star warps space-time deeply, time crawls. You are not separate from space-time. You are inside it. Your body moves along paths determined by the geometry around you. Your time flows according to how space-time stretches or compresses. Your life is a line drawn into the fabric. Everything you see, every motion you make, every breath you take occurs inside a structure that bends. Each moment is shaped by gravity. When you climb a mountain, your time accelerates. When you descend into a valley, your time slows. You do not feel this change, but atomic clocks do. The universe always keeps the exact accounting of space-time. We tend to imagine space as empty, but emptiness is alive with geometry. Emptiness shapes your time. Now picture a planet with mass far greater than Earth. Its curvature of space-time would be deeper. The flow of time near its surface would slow dramatically. A clock there would tick noticeably slower than an identical clock far away. 2 people could begin their lives at the same moment, one on that massive world and the other in the emptiness of deep space. After many years, they would be different ages. Their bodies would have lived through different amounts of time. Their futures would no longer match. This is not a science fiction idea. This is physics. Time dilation is a direct consequence of the geometry of space-time. Where curvature increases, time slows. Where curvature weakens, time speeds up. Mass decides the shape. The shape decides the flow of time. Think of every journey you have ever taken: walking across a room, driving down a street, flying above clouds. Every motion you make traces a path through space-time. Every path is a line drawn across a surface you cannot see. That surface is constantly responding to mass and energy. Space stretches, time bends, reality shapes itself around the presence of matter. Gravity is not invisible hands pulling you downward. Gravity is you walking along the shape of space-time. When you drop a stone, the stone is not falling. The stone is simply following the shortest path through the curved fabric of the universe. The same is true for the moon orbiting Earth and Earth orbiting the sun. None of them is being pulled. They are all following curves drawn by mass. You are a traveler moving along a path carved by gravity. Every moment you live exists inside that curvature. Time bends, space bends. The universe is geometry. And if geometry can bend, the possibilities become astonishing. We can imagine deeper curves, sharper wells, regions where time nearly stops. Somewhere in the universe, the fabric is pulled so tight that the curve becomes a cliff, a wall, a one-way edge. But before we reach those extremes, one question remains. If gravity bends time, how much can time bend? How slow can time become? How far can the fabric stretch before it breaks? We are about to find out. Gravity does not pull you. Gravity guides you. That sentence can change the way you see the world if you let it sink in slowly. When you walk, you are tracing a path through space-time. When a planet moves through the void, it follows the same kind of path. These paths are not chosen. They are dictated by geometry. You are following the curve drawn by Earth. The moon follows the curve drawn by the sun. Everything follows the shape of the fabric beneath it. Einstein used a word to describe these natural paths: geodesics. A geodesic is the straightest possible line through curved space. If space were flat, a geodesic would look like the straight line you learn to draw in school. But if space is curved, then what appears straight in that curved world may look bent to us. Think of an airplane traveling around Earth. From the perspective of a globe, its path might appear curved. But if you lived on the surface, that curved path might be the straightest one available. Two-dimensional creatures living on a balloon would have no idea that their straight paths were actually curved in 3 dimensions. In the same way, we cannot easily see the curvature of space-time because we live inside it. Objects do not choose curved paths. Curved space-time draws the paths for them. This shift of understanding frees us from a misunderstanding that lasted for hundreds of years. Gravity is not a force pushing or pulling anything. Gravity is the consequence of space-time telling matter how to move. Matter is not compelled. Matter simply obeys the landscape beneath it. A dropped stone is not falling. It is moving along a geodesic. It is falling only because our intuition tells us there must be a force dragging it down. But the stone is obeying the shape of space-time. Its motion is the natural outcome of geometry. Now imagine that space-time is a living surface. All around you, space-time flexes gently under the influence of Earth's mass. The fabric dips under your feet. It dips more deeply beneath the ocean. It dips further beneath mountain ranges. These dips are shallow compared to what massive stars can create, but the principle is universal. Where mass concentrates, space-time curves. Where space-time curves, time slows. The two are inseparable. When you stand near the surface of Earth, time runs slower for you than it does for someone far away in orbit. You may think of astronauts as simply floating in space, but they are experiencing a slightly different reality. They age differently. Their seconds stretch in a subtly different rhythm. They are living inside a slightly faster flow of time. When Einstein understood this, he realized that time itself is part of the architecture. If space bends, time bends. If gravity changes space, gravity changes time. You cannot separate them. Space and time are bound together into space-time. When mass curves space-time, clocks respond. They do not ask why, they do not resist. They simply tick according to the geometry around them. Once you accept that time is part of the geometry, everything becomes clearer. The bending of time is unavoidable. You cannot protect yourself from it. You cannot sense it with your body. Your entire existence happens inside it. You age according to your trajectory through space-time, not according to some universal clock. We are trapped inside a curved fabric that constantly shapes our experience of reality. Think of the surface of a calm lake. Smooth, still, a perfect reflection. Now imagine a heavy stone dropped into the lake. Ripples spread. The surface changes shape. Space and time behave the same way. A massive object enters space-time and ripples spread. Those ripples are gravitational waves. They carry information about the movement of massive bodies. They travel outward like ripples on water, except they pass through everything, including entire planets, without stopping. In the early years of the 21st century, scientists built one of the most sensitive instruments ever created. 2 long corridors stretching for kilometers ended at mirrors that could detect the tiniest tremor in space-time. One night, space-time rippled. The mirrors shifted. The pattern matched exactly what Einstein predicted. 2 black holes far away had spiraled into one another, releasing energy not as light, not as heat, but as pure curvature of space-time. Reality shook. We felt it. When scientists analyzed the signal, they realized they had recorded something astonishing. The collision released energy equivalent to converting a few times the mass of our sun directly into gravitational waves in less than 1 second. Not photons, not particles, pure geometry changing shape. Einstein was right. The universe does not use force to move matter. The universe uses shape. The more massive something becomes, the deeper the curve it carves into space-time. Imagine a bowling ball pressing into a mattress. Now imagine replacing the bowling ball with a star. Picture the fabric sinking deeply. Then imagine swapping the star for something far denser. A collapsed star or a neutron star. The curvature deepens dramatically. If you replace that collapsed star with an even more extreme object, a black hole forms. There, curvature becomes so steep that time nearly stops. The road from a falling apple to a collapsing star is paved with geometry. You are standing on a world where the fabric is gently curved. Time is slowed, but not dramatically. Your seconds feel regular because everything around you shares the same curvature. Everyone near you is aging at nearly the same rhythm. But if you traveled to a stronger gravitational well, you would not. Imagine descending toward the surface of a neutron star. The mass of our sun compressed into a sphere only a few tens of kilometers wide. The curvature there is so intense that space slopes downward like the inside of a well. If you hovered near its surface, time for you would slow dramatically compared to someone far away. Hours for you would be days for them. You would not feel time slowing, but when you returned home, others would be older while you remained young. This is the power of curved space-time. Time dilation is not a trick. It is not an illusion. It is the direct expression of geometry. Gravity stretches time. Time responds to mass. Most people think of time as something that flows without choice. Einstein revealed that time is not the flow. Time is the ground beneath us. We are not drifting through time. We are walking on the structure of space-time, and the structure determines our pace. The next realization is even more mind-bending. If time can stretch gently under normal gravity, then what happens when gravity becomes extreme? What happens at the edge of a black hole where space-time curves so sharply that not even light can escape? If gravity is geometry, then a black hole is geometry pushed to its limit. Next, we explore how time behaves near the steepest curvature in the universe, where seconds stretch into eternity, where the future for one observer becomes the past for another, where time nearly stops. Gravity deepens, space-time bends, time slows. And there is a point where slowing becomes something stranger, a place where time stretches so far that a single second near an extreme mass can equal years for someone far away. But before we reach that abyss, we must finish understanding the geometry itself. Because without truly grasping that gravity is not a force, the next chapters will feel like magic instead of logic. Picture yourself floating far from any mass. No planets, no stars, no motion beyond gentle drifting. You release an object next to you. It does not move. There is no curve in space-time to guide it. The fabric beneath you is flat. Nothing warps it. Time flows freely. Space remains open. You and the object remain side by side, suspended in emptiness. Now imagine that Earth appears beneath you. The fabric bends. Not a tug, not a pull, a slope. Your object begins to slide along the curve of space-time. You begin to slide along that same curve. You call it falling. But what is really happening is that you are both following geodesics, the natural paths through curved space-time. You are not being forced, you are obeying the terrain. Space beneath you fell inward toward Earth, and you followed. The deeper you descend into the curve, the slower time flows for you. Every meter toward Earth's center means stronger gravity, more curvature, slower time. A clock set at the bottom of a deep mine runs slower than a clock at the top of a skyscraper. This is not imagination. This is measured reality. The difference is small because Earth is not massive enough to carve a deep well in space-time. But the principle holds. A deeper curve means slower time. A shallower curve means faster time. This leads to a powerful realization. There is no universal time. There is no moment that everyone shares. Time flows differently depending on the geometry you are inside. If you climb a mountain, you age slightly faster than someone living at sea level. If you travel into orbit, your aging speeds up even more. If you plunge toward a massive star, your time slows dramatically compared to distant observers. All of this emerges naturally once we accept that gravity is geometry. To feel this more deeply, imagine a sheet of thick rubber stretched tight. You place a heavy ball in the center. The ball sinks into the rubber. Now roll smaller marbles around the indentation. The marbles follow curved paths. The deeper the indentation, the more dramatic the curve. If the indentation becomes steep enough, the marbles cannot escape. They spiral inward. That is how orbits work. Planets are not held by some cosmic chain. They are simply following the curve carved by the mass of a star. Earth is not pulled by the sun. Earth is falling around the sun. The fall never ends because Earth has sideways motion. If that sideways motion vanished, Earth would drop directly toward the sun. If the sideways motion increased dramatically, Earth would escape the curve entirely and drift into interstellar space. Everything becomes motion along the shape. Geometry rewrites every force we once believed in. Einstein's insight solved mysteries that Newton could not. The orbit of Mercury, for example, shifts slightly each century. Newton's equations could not explain this shift. Einstein used curved space-time and solved it instantly. No force, no invisible pull, just geometry. When we accepted this, the universe opened. If gravity is geometry, then time is not an independent thing. Time is part of that geometry. Time shifts when the geometry shifts. Time slows when space-time dips. Time speeds up when space-time relaxes. You and everything around you exist inside a river of space-time. But that river is not smooth. It flows differently depending on where you stand. Here is the final step that completes this chapter. The moment gravity becomes extreme, time begins to behave in ways that stretch our understanding of reality. Imagine a neutron star, the mass of our sun crushed into a sphere only a few tens of kilometers across. The curve it creates in space-time is so deep that time near its surface runs dramatically slower than time far away. If you hovered near such a star for a single hour, someone far from that gravity well would experience many hours or even days. When you returned, you would find a universe slightly older than you expected. You would have lived less time than the people you left behind. Not because your clock malfunctioned, not because you slept, because time itself ran differently for you. That is the true power of geometry. Time changes for those who stand in different shapes of space-time. Now push this idea further. Imagine a place where the curve becomes impossibly steep. A place where space-time dips downward without end. A place where motion cannot escape the slope. A place where time slows so dramatically that it nearly stops when viewed from outside. That place exists. We call it a black hole. A black hole is not a thing. A black hole is a shape. A curve so deep that the fabric folds toward it. The geometry becomes extreme. Once something crosses the edge, called the event horizon, it is swallowed not by a force, but by the shape of space-time. Inside that region, all geodesics lead inward. Even light cannot escape. Light, which is the fastest thing in the universe, travels along geodesics too. And inside the extreme curvature of a black hole, every possible path leads toward the center. Time near that edge slows to an almost unimaginable level. To someone at a safe distance, watching you descend toward the event horizon, your time appears to slow. Your motion appears to freeze. They see you stretch and fade. You appear to hover forever on the edge. But from your perspective, time continues normally. You see your own clock ticking. You cross the event horizon without noticing anything special. Two realities occur at once, both true, both valid, both consequences of geometry. Time is not universal. Time is personal. Gravity is not a force. Gravity is geometry. You are not moving through time. Time is moving around you. The fabric of space-time responds to mass. Mass shapes the flow of time. And if gravity can slow time here, then in the deepest gravity well, time can nearly stop. In the next chapter, we step into that well. We explore how gravity slows time and how Einstein predicted this over 100 years ago. We will watch clocks disagree. We will watch seconds stretch. We will watch time reveal that it is not an illusion. Time is structure. Time is shape. Time is curved. Time does not behave the way we believe it does. It does not treat every location equally. It does not flow at the same rhythm throughout the universe. It stretches. It compresses. It responds to gravity in a way that rewrites our understanding of reality. To begin, imagine placing two identical clocks side by side. They tick together, perfectly matched. Now lift one clock higher, even by the height of a desk. Over time, the higher clock will tick slightly faster. Not because the mechanism changed, not because anything interfered, but because the clock is experiencing weaker gravity. Even a tiny difference in gravity changes the rate of time. Einstein predicted this without touching a clock. He predicted it using thought alone. He imagined a universe where gravity is geometry, and time is woven into that geometry. If gravity bends space-time, then time must bend along with it. That idea sounds poetic, but it leads to a precise conclusion. Closer to mass, time slows. Farther from mass, time speeds up. This effect is called gravitational time dilation. Think of a hill. At the bottom of the hill, the slope is steep. At the top, it becomes gentle. Time flows like water down that slope. The deeper you go into gravity, the slower time runs. Gravity is not pushing on time. Time simply follows the shape of space-time. When the curvature becomes deeper, the flow of time becomes thicker and slower, like syrup on a cold morning. This means something shocking. There is no universal second. A second for you is not the same second for someone else. The universe is filled with different pockets of time, each ticking at its own rhythm, shaped by the mass around it. A second near the surface of Earth is ever so slightly longer than a second on a tall mountain. A second near the surface of a dense star is far longer still. The stronger the gravity, the slower the time. Einstein reached this idea by asking a deceptively simple question. What happens to time inside an accelerating elevator? If you stand in that elevator and it begins to accelerate upward, you feel pressed down. A coin released from your hand falls to the floor. Inside that elevator, the coin falls because the floor rushes upward to meet it. Einstein realized that to the person inside the elevator, the experience is identical to gravity. There is no difference between being pulled by gravity and being pushed by acceleration. From this, Einstein made a bold leap. If acceleration can slow time, then gravity must slow time. Gravity and acceleration are not similar. They are the same phenomenon. Time reacts to gravity because time reacts to the curvature of space-time. You cannot separate space from time. You cannot separate gravity from time. They are inseparable pieces of the same structure. Now imagine taking two clocks. You leave one on Earth. You send the other far into space, beyond Earth's gravitational influence. You bring it back later and compare them. The clock that stayed on Earth will show less time has passed. The clock farther from gravity aged more. Its time flowed faster. The difference can be small or enormous, depending on how strong the gravity difference is. But the result is always the same. Time slows in gravity. The difference is so real that modern technology depends on correcting it. Satellites orbiting Earth experience weaker gravity than we do on the surface. Their clocks run faster. If we did not correct those clocks, systems that rely on exact timing, like the global positioning system, would fail. Time dilation is not philosophy. It is not a theory waiting for confirmation. It is a measurable fact. But before we reach satellites and technology, consider how time responds to extreme mass. Imagine standing near the surface of a huge star, something many times more massive than our sun. The curvature of space-time becomes deep. Time slows noticeably. If you stayed near that star for a few hours, you could return to find that many more hours passed for those who remained far away. You would have lived through fewer moments of time. This becomes even more dramatic near neutron stars, where the mass of a star is compressed into a sphere only a few tens of kilometers across. The curvature there is intense. Time runs much slower. A person hovering near a neutron star for a short time would return to Earth to discover that days or weeks have passed. Time becomes unbalanced. Reality becomes uneven. Einstein once said that people who believe in physics understand that the division between past, present, and future is only a stubborn illusion. Time dilation shows us why. Your past and someone else's past do not link together neatly. Their flow of time and your flow of time diverge. The universe does not share a single clock. Every mass writes its own rhythm into space-time. The deeper we go into gravity, the slower time flows. Somewhere in the universe, there exist regions where gravity bends space-time so intensely that time nearly stops. We call those places the edges of black holes. You do not feel time slowing. You cannot sense the change. Your heartbeat and thoughts proceed as usual. That is what makes this so strange. Time dilation is silent. It does not warn you that your seconds are stretching. The universe simply changes the rhythm of your time without asking for permission. Imagine holding a flashlight and pointing it straight upward. Light climbs away from Earth. As it rises into weaker gravity, the light subtly shifts to a slightly lower frequency. Physicists call this gravitational redshift. The light's wavelength stretches because light is experiencing time differently as it escapes stronger gravity. Even the vibration of light changes its rhythm depending on the flow of time. If something as fundamental as light is affected, then everything is. Time dilation is not an effect on clocks, it is an effect on time itself. The clock only reveals what space-time is doing. Here is a more vivid way to feel this truth. Imagine two people standing on a tall tower. One remains at the top, the other takes the elevator to the ground floor. If they both start stopwatches at the same moment, then reunite hours later and compare them, The stopwatch that stayed higher will show slightly more elapsed time. The difference is tiny, but it will be there. The person at the top aged a little faster. Not enough to notice, but enough that physics can measure it. Every step you climb up a staircase takes you farther from Earth's center. Each step puts you into a slightly weaker gravitational field. Each step speeds up your time. You age faster on the top floor of a building than on the ground floor. The effect is microscopic, but real. Now stretch this idea to astronomical scales. Imagine you descend from orbit toward a massive planet. As you fall, gravity intensifies. The curvature of space-time deepens. Your time gradually slows compared to someone who remains far away. If you hovered over the surface, stayed there for a year, then returned to the person in orbit, you would discover that the person in orbit aged more. They would have lived more minutes, more hours, more days. Their time flowed faster. That is the universe. Every location has its own time. There is something beautiful in that. Time is not a singular river that carries everything along. Time is more like countless small streams flowing through the landscape of space-time. Mass shapes the terrain. Each path is different. Each flow is personal. Understanding this leads to a deeper question. If gravity slows time, what happens when gravity becomes unimaginably strong? How slow can time become? Is there a limit? Can time reach zero? To explore that, imagine going to a neutron star. A neutron star is one of the densest objects the universe can create without collapsing into a black hole. It contains the mass of our sun crushed into a sphere only a few tens of kilometers across. The surface gravity is millions of times stronger than Earth's. The curvature of space-time is fierce. If you hovered above that surface, time would slow dramatically for you. Hours would pass for you, while days passed for others far away. In that place, time feels thick. Your thoughts seem normal. Your heartbeat is steady. Your mind does not feel stretched. But space-time is shaping your moments into longer intervals. You experience less time because you are inside a deeper well. From far away, someone watching you would see your motion slow. If they sent you a video of themselves, you would watch it at a faster rate. They would be moving too quickly because their time is flowing faster. Both of you would be correct from your own perspective. Both perspectives would be true. Time dilation creates different realities that exist simultaneously. Einstein realized this and expressed it in a sentence that deeply unsettles anyone who reads it with full attention. He said that the separation between past, present, and future is only a stubborn illusion. When time is relative, the idea of a single present moment dissolves. You live in your own rhythm of time. Others live in theirs. There is no single universal now. When we pull this idea to its extreme, we reach the most disturbing possibility. A place where gravity stops time almost completely. A place where the flow of time becomes infinitely slow. A place where someone watching from a distance sees time stretch endlessly. That place exists. It is the edge of a black hole. A black hole is not simply a dense object. It is a region of space-time where curvature becomes so steep that all paths lead inward. Nothing escapes, not even light. At the edge of the black hole lies a boundary called the event horizon. At the event horizon, the flow of time becomes so distorted that from the outside vantage point, time appears to freeze. If you hovered just above the event horizon, seconds for you would be unimaginably longer than seconds for someone far away. Hours could pass for them, while only moments passed for you. If you drifted slightly closer, the difference would grow even more extreme. Go closer still, and from the perspective of the outside universe, time for you would approach zero. From outside, it would look as if you never quite reached the horizon. You would appear stuck, suspended, frozen in place. Your motions would slow. Your voice would stretch. Your image would fade. From your perspective, you would experience nothing unusual. You would see your own clock ticking normally. Your mind would think normally. you would simply cross the horizon. You would cross the point of no return. Two realities exist. Both are true. The outside world sees time slowing to a stop. You experience time normally, unaware that the universe has divided its realities between your perspective and theirs. That is the ultimate conclusion of gravitational time dilation. Time does not only stretch. Time does not only slow. Time can fracture realities. When Einstein first wrote these predictions, they seemed impossible. But every experiment we perform proves them. Every clock we place in a different gravitational field confirms them. Every observation of stars orbiting the center of our galaxy verifies them. Time is not a constant. Time is a shape, sculpted by gravity. And now that we understand how gravity slows time, we are ready for the next proof. We will leave theory behind. We will launch a clock into space. We will watch time itself change. Next, we witness the experiments that proved Einstein right. Time dilation was once just an equation on a piece of paper, something written in quiet symbols that few people understood. Einstein had no spacecraft, no satellites, no atomic clocks to test his idea. He had only logic. He sat in a silent office in Bern and imagined elevators falling, beams of light bouncing between mirrors, and observers in motion disagreeing about when events occurred. He pushed thought as far as it could go, and what emerged was a prediction that sounded impossible to anyone raised on Newton's certainty. Gravity slows time. For years, no one could prove it. The difference in time flow between sea level and mountaintops was far too small for any clock to detect. But as technology improved, we reached a moment when the universe allowed us to witness the bending of time directly. The first great test happened many decades after Einstein's prediction. Scientists placed an extremely precise clock on a rocket. They strapped the clock into a capsule and launched it upward. The rocket climbed through Earth's gravity. As it climbed, the clock entered a region where gravity weakened. The curvature of space-time relaxed. Time flowed slightly faster. On the ground, another identical clock remained. It continued ticking inside stronger gravity. Its time remained slower. When the rocket returned, the clocks were compared. They disagreed. The clock that traveled upward into weaker gravity had aged more. Its time had flowed faster. Einstein had predicted the exact amount of difference decades before this experiment. The universe matched his numbers perfectly. Gravity did not slow the mechanism of the clock. Gravity slowed time. The mechanism only revealed what space-time had done. Later, scientists repeated the experiment on airplanes. They placed one atomic clock on a fast-moving jet and flew it around the world. They left an identical clock on the ground. When the flight ended, the clocks were compared. Once again, the traveling clock showed a different amount of elapsed time. Not because of acceleration alone, but because motion and gravity each play their own role in shaping time. Every test, every experiment, every precise measurement gives the same answer. Time is not universal. Time is personal. Time responds to gravity. The most delicate test of all took place in a laboratory using two atomic clocks placed just a short distance apart, one only slightly higher than the other. The difference in elevation was not the height of a mountain, not the height of a building, not even the height of a tall desk. The elevation difference was less than 1 meter. The higher clock ran faster. No human could feel the difference. No muscle in your body could sense the extra aging. But the universe keeps perfect accounting. The flow of time depends on location, and location depends on gravity. Once you understand this, something inside you shifts. Time stops feeling like an invisible river that moves us all together. Instead, you begin to see time as a landscape, shaped by mass and curved by gravity. You understand that your life is not lived along a shared timeline. Your life follows a personal stripe of time carved into the geometry of space-time. Every choice you make draws a new line. Every motion bends your trajectory. Every moment you exist becomes part of the structure of the universe itself. Time dilation is real not only at cosmic scales, but here, now, on Earth, in your daily life. You age slower the closer you are to Earth's center. You age faster the higher you stand. If you spend years at high altitude, you accumulate slightly more time than someone who spends their life at sea level. You will have lived more moments. The difference will never be felt emotionally, but it exists physically. In the heights of space-time near a black hole, the change becomes extreme. But even here on Earth, the bending of time operates constantly, silently shaping your existence. Einstein once wrote that the most incomprehensible thing about the universe is that it is comprehensible. The universe does not hide its truths. It simply waits for us to notice them. At this point, it becomes fair to ask a difficult question. If time is not constant, then what exactly is time? We treat time like a flow, but it is not flowing. We treat time like a force, but it is not pushing. We treat time like a measurement, but it is not measuring. Time is part of the geometry of space-time. It stretches, it bends, it changes depending on where you stand. To accept gravitational time dilation is to accept that reality does not unfold in a neat sequence of shared moments. Reality is stitched together by countless personal experiences of time, all shaped by mass and motion. Each of us is living in our own timeline, overlapping but not identical. A person on a mountain has lived slightly more time than someone in a valley. A person on a jet has lived slightly less time than someone waiting on the ground. Astronauts on the International Space Station experience time differently from us. Their clocks must be corrected so that the signals they send remain synchronized with clocks on Earth. Time is a dimension that reveals itself through the way it curves. Einstein's equations predicted something else as well, something far more intense, something that sits at the edge of reality. There is a point where curvature becomes so extreme that time does more than slow. It stretches towards stillness. Imagine standing at the top of a deep well. If someone at the bottom shouts, the sound struggles upward. Time behaves the same way near enormous mass. If you hover just above the surface of a neutron star, time for you slows so dramatically that an hour for you could be many hours for someone far away. And if you go beyond that, if you descend farther into the well, if you approach the steepest curvature space-time can form, you reach the event horizon of a black hole. At that boundary, gravitational time dilation reaches its limit. From the outside universe, you appear to be moving slower and slower. Your time is being stretched so far that it seems to nearly freeze. The person watching from a safe distance will never see you cross the horizon. You will appear to fade. You will appear to stop. For them, time has halted for you. But from your perspective, nothing unusual happens. You do not feel time slow. You do not notice the bending. You simply cross the horizon. 2. Realities. Both true. Time dilation does not simply alter minutes or hours. It alters the nature of reality. It splits the universe into different perspectives, each one valid, each one shaped by space-time. Gravity slows time. This is not a theory. This is a fact written into the structure of the cosmos. And now that we understand the bending of time, we can witness how humanity uses this bending every second of every day without realizing it. In the next chapter, we leave experiments and step into daily life. We discover that the system guiding every airplane, every ship, every delivery truck, every map on your phone works only because time runs differently in space. For most of human history, time was measured by shadows and sand. Sundials carved out daylight into rough intervals. Sand poured from glass bulbs, marking moments that slipped quietly away. Even mechanical clocks with their gears and pendulums never came close to perfection. Time was something we could feel, but never truly measure. When Einstein proposed that gravity slows time, he was making a claim far beyond what any technology of his day could test. In the early 1900s, there were no instruments sensitive enough to detect differences as small as a few billionths of a second. Even if someone wanted to test Einstein's prediction, There was simply no clock accurate enough to reveal the truth. His idea had to wait for technology to evolve. Decades passed. Humanity built machines more precise than anything Einstein ever saw. We split atoms, measured starlight, and launched rockets beyond the atmosphere. The search for accuracy pushed engineers and physicists to build a device unlike any clock that existed before. This device did not rely on gears or springs or pendulums. It measured time through the vibration of atoms. Atoms vibrate with perfect regularity. They form nature's metronome. Scientists discovered that certain atoms, such as cesium, vibrate an exact number of times per second, always the same no matter where the atom is or what it experiences. By counting these vibrations, we gained access to the most precise rhythm in the universe. This became the atomic clock. An atomic clock is not special because it moves quickly. It is special because it barely drifts. If an atomic clock ran for millions of years, it would lose less than a second. It measures time with such precision that even the smallest disturbance becomes visible. A slight change in temperature, a tiny shift in pressure, even microscopic vibrations in the ground can introduce errors. The precision required to operate one demands careful isolation. They are placed on vibration-free platforms and held inside controlled chambers. Everything must remain still. Now imagine using that level of sensitivity to test Einstein's prediction. If gravity slows time, then a clock placed deeper in Earth's gravitational field should run slightly slower than an identical clock placed higher. The difference would be unimaginably tiny, far too small for any mechanical clock to detect. But atomic clocks changed that. Suddenly, we could test whether time itself bends. In the 1970s, a group of scientists developed an experiment called Gravity Probe A. They built one of the most accurate atomic clocks ever created. They placed it inside a small spacecraft, sealed it carefully, and launched it upward on a rocket. The plan was simple. Let the clock travel into weaker gravity, compare its time to a clock that remained on the ground, and check the difference after the flight. The rocket carried the clock thousands of kilometers above the surface of Earth. The altitude placed it in weaker gravity, where Einstein predicted that time should run faster. Down below, a reference clock waited, ticking slowly inside stronger gravity. The clock on the rocket measured the vibrations of cesium atoms as time passed. The clock on Earth did the same. When the experiment ended, scientists compared every vibration recorded. The results matched Einstein's predictions exactly. The clock in space aged more. Its time flowed faster. It experienced more moments of existence. This was not due to motion or error. Both clocks were shielded carefully. The only difference was the strength of gravity. Gravity Probe A proved that time passes differently at different altitudes. Einstein had predicted this half a century earlier, using nothing more than reasoning and mathematics. The universe confirmed him. The rocket experiment was not the end, it was the beginning. Physicists wanted to push further. They wanted to test how sensitive time was to gravity. If a difference of thousands of kilometers produced a measurable change, what about a difference of a few kilometers? What about a difference of a few meters? Could the bending of time be measured inside a single building? In the year 2010, scientists performed a new experiment using two atomic clocks placed only a short distance apart. One clock sat on the floor. The other was lifted onto a shelf less than 1 meter above it. They let both clocks run. After a period of time, they compared them. The clock on the shelf ticked faster. The difference was incredibly small, but measurable. This was the first time in history that the effect of gravity on time was measured over an elevation difference small enough to fit inside a room. Time dilation was no longer something that belonged to black holes and distant galaxies. It existed between the floor and the ceiling. This is where Einstein's idea becomes personal. You age faster standing on the top floor of a tall building than you do at the bottom. If you sleep on the second story while someone else sleeps on the first, you experience slightly more time. Over a lifetime, The difference amounts to a fraction of a second, barely enough to notice. But the universe notices. Space-time never loses track of its accounting. Later, scientists repeated a variation of the experiment using airplanes. They placed atomic clocks on commercial jets and flew them around Earth. Another clock remained stationary in a laboratory. When the airborne clocks returned, they showed that time had passed differently. The clocks that traveled experienced a combination of gravitational time dilation and a related effect called time dilation due to motion. Their time slowed in response to both gravity and speed. When the clocks were compared, the readings diverged exactly as Einstein's equations predicted. The more we tested time dilation, the more its truth became undeniable. Every experiment revealed the same result. Time responds to gravity. Time responds to motion. Time is not universal. Time is not constant. Time depends on the geometry of space-time. Yet even after these experiments, the idea still feels unreal. When you stand at sea level, you do not feel time slowing. When you climb a mountain, you do not sense time speeding. You do not feel the warp of space-time. You only feel gravity as weight. You only feel motion as wind against your skin. But time is bending. Time is flowing into different rhythms. Consider what this means. If time can stretch and compress based on where you stand, then time is not an independent quantity. It is part of space-time. You are not moving through time. You are being carried through time by the shape of the universe. The next question becomes unavoidable. If time dilation is real, and atomic clocks prove it beyond doubt, then where in our daily lives do we rely on this effect without realizing it? As strange as it sounds, almost every person on Earth uses time dilation technology every day. Modern navigation and communication would collapse without it. Airliners would not reach their destinations accurately. Delivery routes would fail. Rescue teams would get lost. Your phone would show the wrong location. To understand why, imagine a satellite orbiting Earth. It carries atomic clocks inside. These clocks tick in weaker gravity and at high speed. Because of weaker gravity, the clocks run faster. Because of high speed, motion slows them. Both effects happen at the same time with different magnitudes, and both must be corrected constantly. If engineers did not compensate for gravitational time dilation and the time dilation caused by motion, location signals transmitted from orbit would drift. Within a single day, an uncorrected system would produce location errors of many kilometers. Every time you check a map on your phone, you are relying on Einstein's insight. The satellites orbiting Earth must be calibrated so that their clocks match clocks on Earth's surface. Computer systems constantly apply corrections based on general relativity and special relativity. If they did not, navigation would fail. Time dilation is not merely theory. It is infrastructure. Einstein showed that clocks are not measuring something external. They are participating in the behavior of space-time itself. When clocks disagree, they are not malfunctioning. They are revealing the shape of the universe. Time dilation experiments forced physicists to confront something uncomfortable. If time depends on motion and gravity, then time does not exist independently of the observer. There is no universal present moment shared by everyone. There are only personal timelines shaped by space-time. Every atomic clock tells the truth of its own path through the universe. This means something profound. When two clocks move differently or sit in different gravitational fields, they do not stay synchronized because they do not experience the same reality. The universe has no master timekeeper. Every observer experiences time according to their motion and location. Einstein once wrote that our separation of past, present, and future is only a stubborn illusion. Time dilation experiments confirm this. They show that time is not a straight line. Time is a dimension woven into the structure of space-time. When space-time bends, time bends. When space-time stretches, time stretches. You exist inside that curvature. The atomic clock experiments proved that Einstein was right. Not by thought, not by philosophy, but by measurement. Gravity probe. A lifted a clock into weaker gravity. It returned with more time. Airplanes carried clocks across the sky. They returned with different amounts of time. Clocks separated by less than a meter ticked at different rates. The universe responded to every test the same way. Time is not universal. Time is not constant. Time is geometry. Once we accept this, a new possibility emerges. If satellites must correct their clocks because time runs differently in space, then systems that guide airplanes, ships, trucks, and emergency responders rely on the stretching of time. Without relativity, global navigation would collapse. Einstein's idea is not a curiosity. It is the foundation of modern life. The bending of time is no longer a mystery. It is a tool. In the next chapter, we will follow that tool into orbit. We will see how satellites continuously adjust their time so that your location on Earth remains accurate. We will learn that every time you search for a destination, your future depends on the fact that time runs differently in space. Nearly every person alive today uses a technology that depends on Einstein's discovery that time does not flow evenly everywhere. We use it to find our way to unfamiliar streets, to guide airplanes across oceans, to synchronize delivery routes, to track storms, and to allow emergency responders to reach those who need help. We carry this technology in our pockets without thinking. When we open a map on our phone and it shows our position on Earth within a few meters, we rarely stop to ask how it works. We assume the signal comes from a satellite. We imagine a simple broadcast, like a radio station sending information downward. What we do not realize is that our phone can locate us only because time itself behaves differently for satellites than it does for us on the ground. The satellites that orbit Earth are carrying atomic clocks, and those clocks tick at the wrong pace unless Einstein's equations constantly correct them. The reason they tick incorrectly is that the satellites are experiencing weaker gravity and high orbital speeds. Because gravity is weaker above Earth, time flows faster there. And because the satellites move at thousands of kilometers per hour relative to us, their motion causes time to slow. These two opposing effects do not cancel neatly. One speeds up time, one slows it. Engineers must correct both constantly. If they did not, the entire navigation system would fail. When a satellite orbits Earth, it is not floating in empty space. It is following the curve of space-time carved by Earth's mass. The satellite moves sideways fast enough that its path always misses the planet's surface. It is falling around Earth rather than down into it. To us, it looks as though it is floating, but what actually happens is that the satellite is forever falling along the natural path drawn by space-time. Inside that satellite are atomic clocks, measuring time with the steady vibration of atoms. These clocks are crucial. They send precise timing signals to Earth, and your phone reads those signals to determine where you are. Your phone does not measure distance directly. It measures the delay in those timing signals. The distance between you and a satellite is simply the speed of light multiplied by the time it took for the signal to reach you. If time is wrong by just a tiny fraction of a second, your calculated position will be wrong by hundreds of meters. If time is wrong by a full second, your location becomes meaningless. Now imagine that the satellites orbiting Earth are experiencing time differently than we are. They are farther from the center of Earth. Gravity is weaker at their altitude. Einstein showed that weaker gravity makes time run faster. An atomic clock on a satellite ticks more quickly than an identical atomic clock on Earth's surface. At the same time, satellites travel at thousands of kilometers per hour. Motion slows time. This effect pushes the satellite clock in the opposite direction. Gravity speeds it up. Motion slows it down. Engineers must calculate both effects and then adjust the timing signal the satellite broadcasts. If those corrections were not applied, the timing errors would accumulate rapidly. Every satellite would drift further from accurate time. The navigation system would collapse. Consider what happens without correction. If the satellite clock runs faster due to weaker gravity, then its timing signals reach Earth slightly ahead of schedule. The system on Earth would interpret that as the satellite being closer than it truly is. Meanwhile, time dilation due to motion tries to slow the satellite clock, introducing a different mismatch. The errors do not balance perfectly. They combine into a larger discrepancy. Within a single day, the mismatch would grow large enough to produce position errors of several kilometers. By the end of a week, navigation based on these signals would be completely useless. Airplanes would be off course. Ships would navigate blindly. Rescue teams would be directed to the wrong places. Everything from power grids to banking systems relies on synchronized time. Without relativistic corrections, modern civilization would be thrown into confusion. The only reason the system works is because the designers understood Einstein. Before the first satellites were launched, some engineers doubted whether time dilation would matter. They assumed that Earth's gravity was too weak and the satellite speeds were too modest to create noticeable time differences. But physicists who trusted relativity insisted that adjustments must be built into the system from the start. They were correct. The satellites were launched, the atomic clocks were activated, and the differences in time flow matched Einstein's predictions exactly. The clocks in space ticked at the wrong pace unless relativity was applied. To grasp the depth of this, think of time as a river flowing differently at different altitudes. At sea level, the river flows thicker and slower. At higher altitudes, the river thins and moves faster. Each satellite lives in its own stream of time. The phone in your hand listens to many satellites at once and triangulates your position using the timing signals from each stream. It does not rely on a single satellite. Instead, it measures the tiny difference between arrival times of multiple signals. Those tiny delays are converted into distance. If those delays were even slightly incorrect because of uncorrected gravitational time dilation, your calculated position would drift significantly. Every time you tap a location on your phone, an extraordinary collaboration between space-time and engineering unfolds. The phone asks satellites where they were and what time it was when they transmitted their signals. Each satellite answers with a timestamp. Then your phone compares the timestamps, subtracts the travel delay, and solves a geometric puzzle. It draws spheres around the satellites. Your location appears at the point where those spheres intersect. If time dilation is not corrected, the spheres fail to meet. You would appear to be somewhere else entirely, perhaps kilometers from your true location. If this sounds abstract, imagine an airplane flying in low visibility. It depends on satellite navigation to track its path. The pilots rely on the navigation display to know their distance from runways. Without relativity, the plane's computer would believe it was in a different place. The error would build second by second. After hours of flying, the plane might be off its intended route by many kilometers. Flight paths are calculated with extraordinary precision. Without accurate time, precision disappears. Now imagine emergency responders trying to reach a person in distress. A navigation error could lead them to the wrong street or even the wrong city block. Time dilation is not a detail reserved for physicists. It is a hidden pillar holding up modern civilization. We live in a world where satellites broadcast time, phones interpret time, vehicles depend on time, financial markets synchronize trades through time, and our entire digital infrastructure operates on shared time. If time slips, everything slips. Einstein once said that time is what clocks measure. He did not mean that time is created by clocks. He meant that clocks are the tools we use to detect the shape of space-time. When two clocks tick differently, they are describing different realities. They are not malfunctioning. They are telling the truth about where they are and how space-time bends around them. Think of the satellites as scouts traveling along the fabric of space-time. They move along curves drawn by gravity. They report what time is doing at their altitude and speed. Without these reports, we would lose our ability to navigate. The navigation system we use every day is an experiment in relativity, repeating itself endlessly every second. We are constantly verifying Einstein's theory, not in laboratories, but in the very structure of global communication. This realization changes how we view the universe. We cannot think of time as a perfectly shared rhythm. We must imagine a tapestry woven from personal streams. Space tells time how to flow. Gravity pushes on the tapestry, reshaping every second. Motion pulls in another direction, stretching time differently. At every point in the fabric, time has its own texture. It thickens or thins according to the geometry. Now take a step further. If satellites in orbit experience time differently from clocks on Earth, then astronauts aboard orbiting stations are also aging differently from people on the surface. Their clocks run at a slightly faster pace due to weaker gravity, but at the same time, their motion slows their time. The two effects compete. Depending on the orbital altitude, astronauts can age very slightly slower or very slightly faster than people on Earth. Their flow of time is not the same as ours. Once we fully accept this, another truth becomes clear. There is no single present moment shared by the universe. The now you experience is not the same now experienced by a satellite or by someone standing on a distant planet. Each observer carries a private slice of time, shaped by their path through space-time. We do not live inside time. We live inside personal timelines that only appear synchronized when viewed locally. When Einstein wrote the equations of general relativity, he was not trying to be poetic. He was describing the architecture of the cosmos. Time is not a uniform stage. Time is not a passive background. Time is an active property of the universe. It bends, it stretches. It flows faster or slower depending on where you are and how fast you move. And as strange as that sounds, we have built an entire technological civilization on top of that fact. No one feels time dilation in daily life. Yet without it, our world would collapse into confusion within hours. Every navigation system would point the wrong way. Every automated delivery would misroute. Every synchronized network would lose coordination. Energy grids would destabilize. Communications would slip. Even financial transactions, which depend on synchronized timestamps, would drift into chaos. We depend on relativity not because we desire it, but because reality demands it. The satellites orbiting Earth are not just tools. They are proof. They verify every moment that space-time bends and time bends with it. They show us that the universe is not rigid. The universe is flexible and responsive. Gravity shapes the fabric beneath our feet. Motion stretches the fabric around our path. We exist inside a geometry that is constantly changing, shifting, evolving. Time dilation is not a mathematical trick. It is the logic of the universe. And once we understand that time can stretch, a natural question follows. If time slows near ordinary gravity and satellites reveal that time changes at high altitude, what happens in places where gravity is unimaginably strong? What happens near collapsed stars, where mass has been squeezed into a sphere only a few tens of kilometers across? What happens near the edge of a black hole, where gravity pulls so hard that even light cannot escape? In the next chapter, we travel to places where time slows so much that it almost stops. We will stand near the surface of a neutron star, where 1 hour for us becomes days for someone else. Then we will approach the edge of a black hole. There, time becomes tangled. There, time itself stretches into an eternity. When a massive star reaches the end of its life, it collapses. Its core implodes under its own weight, squeezing matter into a state unlike anything found on planets or even ordinary stars. Electrons and protons are crushed together until the atoms themselves cease to exist. What remains is a sphere of pure neutrons, packed so tightly that a teaspoon of this material would outweigh entire mountains. This object is called a neutron star, and it represents one of the most extreme environments in the universe. If Earth were compressed to the density of a neutron star, it would be no larger than a city bus. A neutron star contains nearly the mass of our Sun, squeezed into a sphere only a few tens of kilometers across. All that mass creates a gravitational field so steep that space-time folds sharply around it. The curvature is intense enough to slow time dramatically. Imagine hovering above the surface of a neutron star. You are suspended in space, held by engines powerful enough to resist the crushing pull of gravity. Your clock ticks normally. Your heart beats steadily. You have no sensation that anything is different. Time always feels the same from your own perspective. But to someone watching from far away, your time is running at a different pace. An hour for you might be many hours for them. The difference does not exist in your body or your mind. It exists in space-time itself. The geometry around you has changed. You are deep inside a gravitational well, and the flow of time is thicker there. Every second stretches. This is not a prediction without evidence. Light escaping a neutron star struggles to climb out of the gravitational field. As it leaves, the wavelength of the light stretches. Scientists call this gravitational redshift. The light loses energy because time itself is stretched near the surface. If you shined a flashlight upward from that height, the beam would climb slowly through space-time, shifting toward the red end of the spectrum as it escaped the star's gravity. Even light must pay a toll to climb out of such a deep well. Time dilation and redshift are the same phenomenon seen through different lenses. One affects the rhythm of existence, the other affects the frequency of light. The environment near a neutron star warps our intuition. Imagine that you and a friend agree to meet again after 1 hour. You descend toward the neutron star while your friend stays far away, perhaps orbiting at a safe distance. After exactly 1 hour on your clock, you return, but your friend has aged several hours more than you have. You have experienced fewer moments of time. Your personal timeline contains fewer seconds. The difference is not imagination. It becomes part of your lived history. You have aged less simply by moving through a region of deeper curvature. To understand the scale of this, remember that time dilation near Earth is incredibly small. Atomic clocks must be exquisitely sensitive to measure it. Near a neutron star, the effect becomes overwhelming. It is as though time becomes heavy. The deeper you descend into gravity, the more time resists moving forward. Space-time is bent like a steep cliff face, and time must climb that cliff. Near Earth, the slope is gentle. Near a neutron star, it is vertical. If we wanted to describe neutron stars without relativity, our words would collapse under the weight of contradiction. Newtonian gravity describes forces, not geometry. But a neutron star is geometry. It is not pulling you down with some invisible tether. It is shaping the very terrain you exist on. You are not fighting gravity. You are attempting to move upward along a landscape carved out of time. Think of time as a river. Far from any mass, the river flows smoothly. As you approach a neutron star, the water thickens. It slows. If you wade too deep, you can barely move. And if you go deeper still, the water nearly solidifies. In that place, time loses its ability to carry you forward at the speed you expect. Neutron stars reveal that time can resist, that time can change, that time has texture. These stars are not stable forever. They spin rapidly, sometimes hundreds of times per second. Their magnetic fields are strong enough to tear apart atoms. Some neutron stars emit pulses of radiation in perfect rhythm as they spin. These pulses sweep across the cosmos like lighthouse beams and reach us as precise intervals of radio waves. Because neutron stars are incredibly stable rotators, these pulses repeat with astonishing precision. Astronomers use them as natural clocks, some of the most reliable clocks in the universe. These cosmic clocks reveal time dilation in another way. When a neutron star belongs to a binary system, orbiting another star or another neutron star, its pulses shift rhythm due to the curvature of space-time. Time runs differently along the orbit, and the pulses tell us what space-time is doing. We use neutron stars as laboratories to test the shape of time. Now imagine going closer. Imagine reaching a point where time slows even more. What if the collapse does not stop? What if gravity becomes so intense that even neutrons cannot resist the crush? The star continues to collapse inward until it forms a region where space-time curves inward so steeply that no path leads outward. This is the birth of a black hole. Near a black hole, time dilation does not merely slow time. It stretches time until the flow becomes nearly motionless from the perspective of anyone watching from a distance. A black hole is not an object. It is a place where geometry becomes infinite. The deeper you go, the more time resists movement. At the event horizon, the point where escape becomes impossible, the river of time ceases to flow outward. It becomes sealed. Neutron stars are the last step before this point. They are the threshold between intense gravity and impossible gravity. They show us the edge where relativity becomes unavoidable. The realization that time is not constant moves from theoretical speculation into measurable reality. When you stand near a neutron star, you are not just seeing the effects of gravity, you are experiencing different time. If you spend a few hours there and return home, you will discover that your personal history contains fewer moments. The universe will have moved on without you. Every person, every clock, every photon in the outside world will have aged more than you. The structure of space-time will have reshaped your life. To understand our future, we must accept that our relationship with time is not fixed. We are not passengers being carried along a universal river. We are travelers walking through personal timelines shaped by choices, motion, and gravity. Neutron stars prove this beyond doubt. They show us that time is malleable. They show us that time can slow. They show us that time does not belong to everyone equally. Yet even neutron stars cannot prepare us for what comes next. Because if mass continues to collapse, the curvature becomes infinite. Time does not simply slow. Time almost stops. The next chapter takes us into that singular region, a place where the geometry of space-time folds into a shape so extreme that all motion leads inward and time becomes deeper than our imagination can reach. We are now ready to approach the edge of a black hole. A black hole is not a thing in the usual sense. It is not an object sitting in space like a planet or a star. It does not have a surface you can touch. It is a region of space-time where gravity curves so sharply that all possible paths lead inward. You do not fall into a black hole in the conventional meaning of falling. Instead, space-time itself flows inward, carrying everything along with it. At the heart of a black hole is a boundary called the event horizon. It is not a wall. It is not a barrier. It is a point of no return, where every possible direction points deeper into the black hole. Even light, which normally travels the fastest possible way through space-time, cannot escape once it crosses that boundary. The presence of a black hole reveals the most extreme consequence of Einstein's idea that gravity is geometry. The geometry near this boundary is so steep that time slows dramatically as you approach it. From far away, an observer would see you descending toward the event horizon, but your motion would appear to slow as you approach the boundary. Your image would stretch and dim, as if someone were dragging you through molasses made of time. The light you emit would shift toward longer wavelengths. What begins as visible light changes to red, then to infrared, then to wavelengths the human eye cannot detect. Eventually, your image fades entirely. From the outside perspective, time appears to stop for you at the event horizon. You never cross it. You become frozen at the border. But that is only one version of reality. From your own perspective, nothing unusual happens when you reach the event horizon. Your heart beats steadily. Your mind processes thoughts normally. Your clock ticks forward. You cross the horizon and continue inward. You do not see time slow. You do not feel the curvature build around you. Time always feels normal to the person experiencing it. But the outside universe experiences your time differently. Two valid timelines emerge. The universe divides into separate truths. This is where relativity becomes something deeper than physics. It becomes a challenge to intuition. The idea that two observers can disagree about something as fundamental as whether you cross the event horizon is difficult to accept. Yet both perspectives are correct. Time is not a single universal structure. It is a personal experience shaped by the curvature of space-time. If you continued inward, deeper into the black hole, the curvature would increase. The geometry of space-time would become more intense. The direction toward the center becomes unavoidable, not because gravity pulls you, but because the shape of space-time contains no other path. The river of space-time is flowing inward, and you are on its surface. The closer you get to the center, the stronger the flow becomes. Eventually, space-time pulls you faster than light can travel outward. At that point, escape becomes mathematically impossible. You are not being sucked inward. You are being carried inward. Black holes do not trap you by force. They trap you by geometry. Imagine a waterfall. From far upstream, the river flows gently. You can paddle in any direction. As the water speeds up, your freedom becomes limited. Eventually, you reach a point where the river flows faster than you can paddle. You reach the horizon. Beyond that point, even if you try to paddle upstream, the river carries you over the edge. A black hole behaves the same way, but the river is space-time, and the current is time itself. At the event horizon, the inward motion of space-time reaches the speed of light. There is no stable orbit there, no suspended position, no escape path. For an outside observer, you freeze at the edge forever. For you, time moves forward normally. Time dilation near a black hole becomes more extreme than anything we encounter anywhere else in the universe. Imagine that you orbit a black hole at a safe distance, where the curvature is intense but not fatal. Your ship maintains a stable orbit, held in balance by speed and the geometry of space-time. You look out the window at the stars. Your clock ticks. Your heart beats. Everything feels normal. But time outside your orbit flows differently. A person far from the black hole watches your clock from a distance. They see that your time runs slower. Perhaps 1 hour for you equals 2 hours for them. You age less. You experience fewer moments. You do not feel the slowdown. But when you eventually leave the orbit and return home, you discover that the outside world has aged faster. Black holes allow us to travel into the future simply by hovering near intense curvature. There is a moment that many physicists consider the most dramatic demonstration of relativity. Imagine a pair of twins. One remains on Earth. The other travels to a region near a black hole, spends time there, then returns. The twin who traveled will be physically younger. Not metaphorically younger. Not psychologically younger. Their biological age will be measurably less. Time dilation leaves fingerprints on biology. It affects atoms, molecules, and cells. It affects aging. Time near a black hole is not simply stretched. It is altered in every measurable way. But there is another consequence, one even stranger. At the edge of a black hole, the flow of time becomes directionless. Inside the event horizon, the inward direction becomes the future. There is no motion that leads outward. The geometry forces time to behave differently. Forward in time means deeper into the black hole. The singularity at the center becomes not a location, but a moment in time. Everything inside the event horizon is moving inevitably toward that moment. Outside the black hole, people see you freeze. Inside, you fall freely. Time chooses sides. The universe contains these regions where time nearly stops. They are not theoretical. We have observed stars orbiting huge black holes at the centers of galaxies. We have measured their motion. We have detected gravitational waves from black hole collisions. Black holes are real structures of space-time, and they are abundant. Once we accept this, we must face a profound shift. If black holes can stretch time to near stillness, then time cannot be what we once believed. Time cannot be an invisible stream through which we drift. Time must be part of the structure of space. And if time is woven into the geometry of space, then the past and future must coexist with the present. In the next chapter, we step into a new idea. If time does not flow, if time is a dimension like space, then the entire history of the universe may exist all at once. The past, present, and future could be part of a single structure. Time dilation is not a trick. It is a clue, a hint that time is not passing. Time is already there. Imagine spreading out a map of the world. Every city, every ocean, every mountain exists on paper at the same time. You can place your finger anywhere on that map. You can move forward, backward, sideways. The map does not change depending on where you point. It does not appear one piece at a time. All locations exist together. Now imagine that the map is not a map of space. Imagine instead that the map is a map of time. The past, the present, and the future are all laid out at once. They do not appear one after another. They already exist. Your movement through time is not the unfolding of events. It is merely your journey across the map. This idea, now supported by relativity, is called the block universe. In a block universe, the past does not disappear. It remains part of space-time. The future does not appear later. It already exists. Our consciousness moves through the structure, experiencing one slice of time at a moment, but the structure itself remains whole. Time is a dimension, not a flow. We think time flows because we experience it from inside. Our memories point backward. Our expectations point forward. But this does not prove that time is moving. It proves only that our minds move through it. In relativity, the universe is not a sequence that updates. It is a four-dimensional structure, with 3 dimensions of space and 1 dimension of time. Space-time contains every event that has ever happened or will ever happen, all woven into a single geometry. Einstein himself hinted at this. After a close friend died, Einstein wrote a letter to his family, telling them not to grieve. He said that death was not truly real. He explained that people who understand physics know that the distinction between past, present, and future is only a stubborn illusion. He was not trying to be comforting. He was describing the logical consequence of his equations. If time is part of space-time, then every moment that ever existed still exists. We do not watch time pass. We are carried along a path that passes through the landscape of time. This idea becomes easier to accept once you realize that simultaneity is relative. 2 observers can disagree on what is happening at the same time. One might say that 2 events are simultaneous. Another might say that one event happened first. Both can be correct because motion through space-time affects what each observer perceives as now. If now depends on motion, then now cannot be universal. There is no single present that belongs to everyone. Once simultaneity becomes personal, the flow of time becomes personal. If every observer has their own present, then the universe cannot have a single unfolding moment. Instead, all moments coexist. The shape of space-time decides how time behaves. Imagine that every event in the universe is like a dot on a sheet. Those dots do not appear one after another. They already occupy their positions. Your consciousness draws a path across the sheet, and that path is your experience. You say that time flows because your awareness moves along the sheet, not because the sheet changes. Think of an old film reel. Every frame already exists. When you play the film, you experience motion. The film itself does not move. Time may behave in the same way. The universe could contain all frames at once. Consciousness is the projector. Our experience of flow is the illusion created by our perception. Relativity supports this view. When masses curve space-time, they change the geometry of the block. When motion slows time, it alters the angle of our path through the block. Time dilation becomes proof that time is not universal. If time were flowing as a physical stream, its rate would be the same everywhere. Instead, time depends on motion and gravity. The speed at which we experience time is simply the angle we take through space-time. A person standing on Earth and an astronaut in orbit are moving through different directions in the block. They age differently because their paths through the block differ. Inside the block universe, nothing truly becomes. Everything simply is. Your childhood exists as part of the block. Your future, decades from now, also exists. You have not reached that part of the block yet, but it is already there. Time is not waiting for you. You are moving through it. The same way a traveler walking across a continent sees new cities appear one at a time, even though all the cities already exist, your consciousness moves across space-time. What we call the future is simply a region of space-time you have not reached. This view challenges our emotional experience. We feel that the past is gone, but physics tells us that the past is simply a different part of space-time. We imagine the future as unknown, but physics suggests it is already written into the block. We imagine the present as unique, but relativity teaches that the present is defined by the observer. One observer's present might be another's past. Another observer could experience what we call the future simultaneously with our present, depending on motion and gravity. When you watch a distant star explode, light from that explosion might have traveled for millions of years before reaching Earth. From your perspective, the explosion happened in the past. But from another perspective, depending on motion and location, the explosion might be happening right now. In the block universe, both viewpoints exist within the geometry. Neither is privileged. No single perspective defines reality. Every event remains part of the structure. Consider two people separated by billions of kilometers. They each experience their own now. Because of the distance and their motion relative to each other, their definition of simultaneous events diverges. In one person's present, the other might not have been born yet. In the other's present, the first might already have lived an entire life. Both are correct. Time is not absolute. It is shaped by space-time. The block universe takes that fact to its logical conclusion. The block universe does not tell us that we are trapped in fate. It tells us that our idea of passing time is incomplete. We experience time as motion because our consciousness cannot perceive the entire block. We see only the slice we are currently in. A fish swimming through the ocean cannot see the whole sea. It sees only what surrounds it. We swim through space-time in the same way. This view becomes even more compelling when considered alongside quantum theory. In quantum mechanics, particles do not have single definite positions until observed. Entire histories are possibilities that become defined only when measured. In the block universe, those histories could all exist in the structure, with consciousness selecting a path through them. Relativity gives the geometry. Quantum theory provides the possibility. Once we accept that time is a dimension, not a movement, we see that the universe does not progress. The universe exists. Every moment of your life exists in the block. Your first breath, your last breath, your turning points and quiet moments. They are all coordinates in space-time. Memory gives us the sense of flow. Anticipation gives us the sense of direction. But the block holds everything. This does not mean our choices are meaningless. Within the block, your future is part of the structure, but it includes your choices. Your decisions are woven into the geometry, just as the path of a river is determined by its landscape. You still choose where to step. The landscape simply contains every possible place to step. Time dilation becomes the proof that we are not living along a universal timeline. We are moving through a structure that contains all time. Time does not pass, we pass. In the next chapter, we examine what this means from a personal point of view. If time is not universal, if time is a dimension, if time is part of the block, then there is no single present, no single now. Each observer carries their own slice of time. We are not sharing one timeline. We are each walking our own. If time is part of a block, then the idea of a universal present must be an illusion. We speak as though there is a single moment that everyone shares. We imagine the world synchronized. We imagine that each person, each place, each distant star is experiencing the same now. But relativity reveals that now is not universal. Now is personal. Consider two observers. One stands on a mountain, the other stands at sea level. They are separated by space but connected by gravity. Time flows differently for them. The person on the mountain ages slightly faster. Their seconds contain slightly more duration. They do not feel the difference. Neither notices anything unusual. But if they were to compare extremely precise atomic clocks, they would discover that the clocks disagree. The clocks are not malfunctioning. They are describing the geometry of space-time at their locations. Their nows are not the same. If we add motion, the effect becomes even more surprising. Imagine one person riding a train and another standing beside the tracks. The train moves at a high speed. As the train passes, both observers see a flash of lightning strike the front and the back of the train. The person standing on the ground sees both flashes at the same time. But the passenger on the train does not. Because the train is moving, the flash at the front reaches them later, and the flash at the back reaches them sooner. The two observers disagree about what happens simultaneously. Neither is wrong. They are living in different slices of space-time. Simultaneity is not absolute. It depends on motion. Once simultaneity becomes relative, the present becomes relative. If two observers cannot agree on what is happening at the same moment, then there cannot be a single moment that belongs to everyone. The present is not a universal event. It is a personal boundary. Each observer slices through space-time at their own angle, creating their own present. This becomes even more striking near strong gravity. Picture someone hovering above the surface of a neutron star. Their time runs more slowly. Their present moves through the block at a different pace. A moment on their clock corresponds to a different span of time for someone far away. If they both look toward the same distant star, they are seeing different moments of that star's history. They are not sharing a present. They are passing through different sections of time. Now imagine a black hole. Near the event horizon, time slows to an extreme. The person far away watches their friend approach the horizon. From the distant viewpoint, time slows. The person seems to freeze. They never cross. But from the viewpoint of the falling person, they cross normally and continue inward. Each observer experiences a different present. They do not disagree because of confusion. They disagree because the geometry of space-time gives each of them a different slice of time. When the present depends on gravity and motion, it becomes personal. Your now is not the same as the now experienced by someone orbiting Earth in a spacecraft. Their clock ticks differently. Their path through the block intersects different points of time. If you could freeze the universe and ask every observer what moment they were living, the answers would not match. There would be as many presents as observers. This is not an abstract thought experiment. It affects your everyday life. When satellites orbit Earth and broadcast their timing signals, their present is not your present. Their clocks are running at a different rate. Engineers must correct for these differences so that navigation systems remain functional. Without correction, the relativity of now would cause our navigation systems to fail. The present on the ground and the present in orbit must be reconciled artificially because nature does not make them match. The block universe model makes sense of this. Each observer moves through space-time along their own path. Their present slides across the block at a different angle. The geometry of space-time determines the angle. Gravity bends the path. Motion tilts the path. Your experience of time is shaped by where you are and how you move. If you speed up, your present rotates. If you climb higher, your present stretches. You are not drifting through a shared river of time. You are carving your own riverbed. Think of the block universe as a colossal sculpture. Every point in the sculpture already exists. You do not sculpt it, you explore it. Your choices determine your path through the sculpture, not the shape of the sculpture itself. The future you have not yet reached is already part of the structure. The past you remember is also there. When you recall a memory, you are not pulling something lost back into existence. You are referencing a different point in space-time. The relativity of now suggests that existence is not linear. It is layered. Each observer carries their own layer, and those layers overlap only locally. When you stand next to someone, your gravitational field and motion are almost identical, so you share nearly the same now. But if you separate by distance or speed, the synchronization dissolves. You drift into different nows. The farther apart observers are, the more dramatically their present diverges. A spacecraft speeding near the speed of light experiences such extreme time dilation that the timeline of the universe might unfold differently for those on board. They could return to Earth to discover that centuries have passed. Their present moved through the block along a different angle. They experienced fewer moments. The outside world experienced more. This is not imagination. It is a measured truth. Time dilation has been confirmed with aircraft, satellites, and laboratory experiments. Clocks flown around Earth return with different accumulated times. If time were universal, such differences could not exist. The existence of measurable disagreement proves that each observer's present is unique. Now leads to a profound realization. If the present is not absolute, then the division between past, present, and future is not fundamental. Those are constructs created by our perception. The block universe holds every event, while our consciousness moves through the geometry. The universe does not have a single timeline. It contains an infinite number of personal timelines, each defined by its own flow of now. In the next chapter, we confront what this means for reality. If time is not universal, if the present is not shared, then nothing is fixed. Reality becomes dynamic. The universe becomes participatory. You are not merely moving through time. Time is moving around you. By now, the idea that time could be flexible may feel less like a theory and more like something inevitable. Once we accept that gravity bends space-time, we must accept that time bends with it. Once we accept that motion changes the rate at which time flows, we must accept that each observer carries a personal timeline. Once we accept that two observers can disagree on simultaneity, we must accept that the present is not universal. These facts are not guesses. They are not philosophical speculation. They are supported by experiments carried out with atomic clocks, spacecraft, satellites, and observations of extreme environments like neutron stars and black holes. They force us to see time differently. Time is not absolute. Reality is not fixed. Our intuition tells us that time moves forward, that moments appear and vanish, that the past dissolves and the future forms 1 second at a time. But physics reveals something deeper. Time is part of the fabric of the universe. The past remains part of space-time. The future is already woven into the geometry. We are not watching time unfold. We are moving along a path through a structure that exists all at once. This realization reshapes more than physics. It changes what it means to exist. When you think of your life as a line moving from past to future, it feels as though you are progressing towards something unknown. When you think of your life as a path through a block of space-time, you see that every moment of your life is already part of the structure. Your first memory and your last breath are equally real within the geometry. You have not experienced them yet, but they exist as coordinates in space-time. You are simply traveling from one coordinate to another. This does not eliminate choice, it clarifies it. Your decisions are not predetermined outcomes handed down by fate. They are part of the path you carve through space-time. The block contains every possible section of the path. Your choices determine which route you take. You are not trapped, you are navigating. Time dilation becomes more than a scientific effect. It becomes a window into the architecture of reality. When time flows differently for observers in different gravitational fields, or moving at different speeds, the universe is revealing that time is not a universal rhythm. Time is a property of space-time. It shifts, it bends, it adapts. Imagine two people taking different roads across a landscape. One walks along a smooth valley. the other climbs over steep hills. Their journeys take different amounts of effort and time. They see different sights along the way. They reach different elevations. Their paths are personal, but the landscape is shared. Time behaves the same way. Each observer moves along their own path through space-time, shaped by gravity and motion, but the larger structure remains. When we push this to the extreme, near a neutron star or a black hole, the flexibility of time becomes overwhelming. Time can slow so dramatically that an hour for one observer becomes days for another. Time can stretch until light itself struggles to escape. Time can nearly stop at the edge of a black hole. These effects are not illusions. They are consequences of the geometry of space-time. This takes us to the most profound question of all. If time is flexible, if it can slow or stretch depending on gravity and motion, then what is time actually? It cannot be a flow. It cannot be a universal river. It must be a dimension, a coordinate, a direction you can travel. Your everyday experience becomes remarkable once you understand this. When you walk, drive, or even sit still, you are always traveling through time, but you are not traveling through the same time as everyone else. Your gravitational environment, your motion, your path through space-time shapes your personal time. When you lie on your back and look at the stars, the starlight you see is not happening now. It is a message from another part of the block. A star 1,000 light years away might not exist anymore in your present. You are seeing a moment from its past. But in the block universe, that moment is still there. You are intersecting its coordinate. Reality becomes layered. Time becomes geographic. When you watch the sunlight spill across Earth, that light left the sun 8 minutes earlier. You are seeing a moment that still exists in space-time. You are reaching back across 8 minutes of the block. Every sunrise is a conversation between moments. Every starlight is a window into the structure. The universe holds all its moments. The block contains them. Your consciousness moves. Einstein once wrote that people like us, who believe in physics, realize that the difference between past, present, and future is only a stubbornly persistent illusion. He was describing exactly this. The illusion is not that we experience time. The illusion is that time passes. Time does not pass. We pass. If we could see space-time from the outside, we would see a vast mosaic. Every event, every moment, every heartbeat, every choice lies in the structure. We would see stars form, planets cool, civilizations rise and fall, not as a sequence but as a whole. We would see the universe not in motion, but in completion. This is what relativity reveals. Time is flexible. Time is malleable. Time is personal. And because time is part of reality, reality itself becomes flexible. The universe is not a machine. It is a landscape. We are not passengers carried along a flow. We are explorers carving paths across the structure. The next time you glance at a clock, remember that the number it shows is not the same for everyone, everywhere. Time is not universal. Time is not constant. Time is not absolute. You are not moving through time. Time is moving around you.